Now that we've covered the basics of probability, different representations of probability and how to calculate them, we now build up to dealing with independent events, conditional probability, and a more HL-specific condition called Bayes' theorem. It's done in a separate video. So first, let's talk about independent events. So if we look at these two case scenarios, you can pause and read them. So the difference between them is that in one, the probability of flipping a coin and rolling a six-sided die, they're completely independent of each other. One event does not impact the other. However, in scenario B, the two events that you're doing do impact each other. So they are not independent events. So independent events, we can talk about them in a worded discussion sense, but also mathematically, there is a significance to them. So we say the two events are independent, but the occurrence of one does not affect the chance of the other occurring. So the probabilities are not impacted by each other. And mathematically, it means that if I take the intersection of A and B, it is simply just the probability of A times the probability of B. Which means that if you are trying to test whether two things are independent, you can actually find the intersection separately and then find the probability of A times the probability of B separately, and then compare, are they equal to each other? If they're equal, then you can immediately conclude that these two events are independent. So this is a very useful test to have and a useful formula to use. So for instance, if a question like this shows up, so you have, it tells you that A and B are independent, such that the probability of A is 0.9, probability of B is 0.3. So because I know they're independent, I know their intersection is just going to be the multiplication of those two. So directly from here, I can just say 0.9 times 0.3 will give me 0.27. So the intersection is just 0.27 without having any extra information about how they behave, how they intersect, what events. I don't need that. I just know that they're independent and I can do that. It also applies to the complement of the event. So I can do the same thing with the complement, 0.9 for the probability of A, times the complement of B, which is 1 minus 0.3, which is 0.7. So that will give me 0.63. And now that means when I get to the union of probability of A union probability of B, we need to use the addition rule. So that would be the probability of A plus the probability of B complement minus the intersection between them. Don't forget the addition rule because you don't want to double count the intersection. So we know the probability of A is 0.9. We know the probability of B complement is 0.7. And we know that their intersection is 0.63. So that will give us 0.97. Do expect that these questions could show up in a paper 1, not only in paper 2. So please recall how to multiply decimals with each other and do these calculations. So from independent events, we move to conditional probability. So conditional probability, you've actually dealt with it, but maybe not recognize that it's a conditional probability. So the idea behind it is that there's a condition to your probability. So it's the probability of an event occurring, given that another event has already occurred. So this is a very important concept. Something, before calculating the probability you want, you're already assuming that something has already happened. So if I say I want the probability of A, given that event B has already occurred, I will write it as probability of A given B. So this line indicates given. And you can do it in a sentence worded method. I'll show you how to do that later. Or in a notation method, but the given is always the second letter. So given that B has already occurred, what's the probability of A happening? And this is the formula we use for conditional probability. So probability of A, given that B has happened, is the probability of A and B happening at the same time divided by the probability of B. Now, why is this the formula? Because now instead of looking at the full sample space like we did before, so instead of dividing the probability of the sample space, you are now no longer looking at the full sample space. Because event B has already occurred, your viewpoint is already restricted only on what's happening in the event B. So it's like looking at a full Venn diagram and only focusing on B at the moment because you're already in a situation where B has occurred. So you're only looking at all the possible ways B has occurred. And then you're considering, okay, now that B has occurred, what's the probability of A occurring? So A occurring, given that B has occurred, so they have to have happened at the same time. So you're looking at the intersection. So this is how the formula is working. So you're looking at when A and B are happening at the same time divided by all the possibilities of B happening, because your condition is that B has already happened, which means by symmetry, or sorry, by rearranging this, we can also rewrite the probability of A given B, sorry, A intersect B as probability of B times the probability of A given B. So this is another way to find the intersection of two events. This has nothing to do with independent events. It's a general formula that you can use. And by symmetry, and what we mean by symmetry here is if I switch the probabilities, I can also say the probability of B given A is the probability of them, again, happening at the same time with intersection, doesn't matter which letter you write first, divided by this time the probability of A, because it's given that A has happened. So the given that condition is always in your denominator. So this condition is always in your denominator. So if I rearrange this also, it will give me that probability of A intersect B is equal to probability of A times B given A. So if we notice, we now have two different ways of finding the intersection of finding A intersects B. So let's apply it to Venn diagrams first. So pause, read this question, try and figure out how to use the formula to answer this. So what I'm going to do is I'm going to word this out differently. What if it was a bit of a worded question? So it would say, find the probability. They would say, find the probability that, given that someone used the cafe, find the probability that they went to buy a book. So I will, if I didn't have these letters specified, I ideally would like to write it out. So I would say, okay, they're telling me, given that someone is using the cafe, so I know I need to write it on this side. So using what's the probability that they also bought a book? So by writing it out, in case your questions are a bit more worded, there are no symbols in there. You can write them out like this and then actually do the formula using the written out method. So you would say, okay, which means I need to find the probability of them buying a book and being in and using the cafe divided by the probability that they're using the cafe. This is useful in questions I've noticed that are related to, for example, picking marbles out of a bag or something. So they become very worded and confusing for students. So writing them out like this and continuing the worded notation rather than symbol notation, it makes it easier for the students to understand what type of calculations they have to do. So a book and a cafe would be 12 divided by the probability of them being in a cafe would be 20. So taking these values, you can do it formula-wise. So the probability of a book and a cafe is you have 50 people. So it is 12 out of 50. And of being in a cafe is 20 out of 50. But if you notice, the denominators cancel out, so you end up with 12 over 20. That's why on the previous slide, for Venn diagrams, you can just take the number of A intersect B divided by the event of B. So this is what you get for the first one, and then for the second one. So again, follows the same idea that when I do B given C, I'm now not looking at I'm only restricting my view to C. And from this C, I need to see when does B occur, and it's 12 out of the 20. So in conditional probability, you're always restricting your view to a smaller space rather than all of the 50. I'm now restricted to only looking at the cafe. That's why this becomes your denominator. This is a question that was on the classworks for the previous lesson. So if you completed parts A, B, and C, there was actually a part D to the question. So if you have time to pause, go back to that question and attempt this part D. So part D was a conditional probability. So given that a student does surfing, find the probability they also do rowing. So again, you write it out using symbols if you want to, or a word problem. So probability that they are doing surfing, find the probability that they're also doing rowing. So I'm looking at the intersection of those divided by the probability of surfing, which means I'm now restricting my view to surfing only. And from this surfing, when are they doing rowing? It's those two, 12 and the 8. So it's going to be 20 out of the 48. In tree diagram, you've also been dealing with conditional probability. You just didn't realize it was that. So notice how the tree diagrams are set up. We always know this is A, not A, B, not B, for example. But if you notice how the B event is set out, B, the probability that you see here is only set out here given that A has occurred. As opposed to here, the event B has occurred given that A prime has occurred. So actually, the probabilities that you have in the second branch are always conditional probability. And then when you reach the end of the branch, it tells you, okay, what's the probability that A and B have occurred? So it's always the intersection. So that takes us to the rule that we had before in here, where we showed the symmetry. So the probability of A intersects B is the probability of B times probability of A intersects B, or this. Actually, this is what we're using in the Venn diagram. So this is another proof that the probability, that the formula works. So these branches are always considered conditional probability because you can only write this probability given that A has occurred. Now, this might be completely independent of A, so they're not related, or it might be influenced by A. So we'll talk about that when we combine conditional and independent. So we know that if I multiply the branches for events A and B, I get the intersection of the probability of A intersect B as probability of A times probability of B given A. So this is the fourth axiom. However, I can also combine it with independent events. So if I know that A and B are independent events, then it tells that P of A intersects B is just basically P of A times P of B. And we know that if they are independent, then this is just basically probability of B. So combining these two, I can then say the probability of A intersect B is equal to probability of A times probability of B. Now, this again leads to theorem 3, which is connected to Bayes' theorem. So this will be explained in more detail in another video. But just to point out that looking at this branch here and this branch here, for example, if you have a Venn diagram, just to quickly visually represent, but again, this is explained in another video in more detail. If I'm looking at the event of A and B, so this would be A and B. So this axiom leads to theorem 3 because if I combine these conditions all together, it tells me that if you are looking for event B, you can look at the condition that A and probability of A given A, B given A happens. So this would be this probability here. So this would be the first one. And then I can also look into the probability of not A happening with B, given that not A is happening. Not A happening and B happening is this portion here. Now, when I combine the beige and the yellow portions together, what I end up getting is the full B altogether. So this is an important rule in Bayes' theorem that you can have a look at later. So this leads to this condition here. All right, let's have a look at a conditional probability on a tree diagram. So just pause, have a read through this question, set up the tree diagram, try to find all the probabilities here. So I already have the tree diagram set up. So the first column represents the train, and this is the train being late. This is not late. And the second one is Florian either being on time or not on time. So the question B is asking that the train is late and Florian is on time. So the train is late is this branch A, and Florian is on time would be B. So I know that for part B, I have to do a multiplication here. So I have 0.3 times 0.6, which is 0.18. Then I have the probability that Florian will make it on time. So without giving any conditions about what happens before, I'm looking at, okay, the train might be late, but she's on time. And then the train is on time and Florian is on time. So I'm looking at two options. So either 0.18 plus the other option, which is 0.7 times 0.9, and altogether that will give me 0.81. Okay. Now it says show that the train being late and Florian being on time are not independent events. So how do we prove that? You first need to find the probability of each one. So the probability of the train being late. So the train being late is the train being late is 0.3. We know that from the question. The probability of Florian being on time, so specifically Florian being on time, we've already calculated, which is in part C. The Florian is on time is 0.81. And now what I'm going to do, I need to find the probability of Florian being late and on time. So that would be the intersection between them. So Florian being late and on time has already been calculated in part B, which is 0.18. So if you think of the conditions for independent events, I'm looking at probability of A times probability of B. So what I'm doing, I want to check the left-hand side and the right-hand side. I have the probability of A, which is 0.3. I have the probability of B, which is 0.81. I have the intersection of them, which is 0.18. So I have these. I have these individually. But I just want to check if I multiply these individually, does it give me the intersection? That's how you prove two events are independent. And if I actually take 0.3 and multiply with 0.81, it does not give me 0.18. So this proves that they are not independent. So you need to show all of these calculations and clearly express that they're not independent. You need to show that when you multiply them individually, it doesn't give you the value of the intersection. So you can actually write out this value if you want to, also 0.243. And then just a quick exercise here on, again, combining conditional and dependent. This is just to familiarize yourself with how the rules happen. So if the events are independent, which we've seen on the previous slides, what will the conditional probability be? Well, I know that it's probability of A intersect B over the probability of B. Because they're independent, I already know that the numerator is probability of A times B over the probability of B, which if I simplify, it gives me probability of A. So generally then, if two events are independent, then probability of A given B is just equal to the probability of A happening. So this is what this axiom was referring to, that if they are independent, then this would just be probability of B, this would just be probability of B complement, because the given is not impacting the probability of B happening. And you can continue with these, prove what they would be, and you would get that the first one would also simplify to probability of B, because they're not being impacted by the condition, because these two are independent. And then this would be A, and this would be B also. So these are some nice results from conditions being independent. And then the next step after doing conditional and independence and so on is to look at Bayes' theorem. So Bayes' theorem looks at what if you have the probability of A given B, but you need the probability of B given A. How would you do it in this case? So that's explained in another video with starting with explaining it for 2 events and then leading up to 3 events, which is the maximum you'll have to do as HL.